Welcome to Structural Dynamics class. In this class, we will discuss some special cases of response spectrum. So, in last class, we have discussed a concept of response spectrum, how response spectrum is developed and how we use the response spectrum in finding out the maximum displacement, velocity and acceleration values for a given structure or before designing the structure. And we also studied about how to find base shear and also base moment. Now, in this one we will discuss some special cases. So, what happens if damping is 0 or if damping is extreme value, or what happens if natural period is 0 or natural period is extreme values, okay, 0 or say infinity. So, special case 1. So, this case is about 0 damping. So, if we look at equation of motion, mu double dot plus cu dot plus ku is equal to minus mug double dot. So, this ug double dot is earthquake force, u double dot g is acceleration, earthquake acceleration. So, now mu double dot plus cu is not there because damping is 0. So, the second term is not there. So, this inertia force plus stiffness force is equal to applied force. Then, if we divide this by mass, what we get is acceleration plus this k by m is nothing but omega square u is equal to u double dot g. Then, if we rearrange these terms, acceleration and ground acceleration together, this is absolute acceleration is equal to minus omega square u. So, the maximum value of this one should be equal to maximum value of this one. So, that means what? Maximum acceleration is equal to omega square times u max. So, what is u max? U max is a spectral displacement. So, we can say that spectral acceleration is equal to pseudo spectral acceleration in case of 0 damping. So, what is pseudo spectral acceleration? Pseudo spectral acceleration is displacement, spectral displacement multiplied by frequency square, that is pseudo spectral acceleration. It is not true for all the cases, but in this special case it is same, that is when damping is equal to 0, spectral acceleration is equal to pseudo spectral acceleration. Actually, this is spectral acceleration. So, the left hand side, so that is equal to pseudo spectral acceleration. This is special case 1 when damping is equal to 0. Now, under light damping case, that means damping is lesser value. So, there we cannot ignore this damping term. So, mu double dot plus cu dot plus ku is equal to minus mug double dot. So, if we divide this by mass, then what we get is acceleration plus 2 zeta omega term into velocity into natural frequency square omega square into u is equal to u double dot g. Now, again if we rearrange this one, the terms will be u double dot plus u double dot g maximum value should be equal to 2 zeta omega square u dot plus omega square u. Now, you can observe in this one important thing is this is velocity, this is displacement, and we are trying for maximum value. Now, when displacement is maximum, velocity will be automatically 0. So, that means what? This term disappears. So, that means what? Even in lightly damping case or lightly damped case, spectral acceleration is equal to pseudo spectral acceleration. So, that means what? For 0 damping case and for lightly damping case, we can consider this one, acceleration is equal to pseudo spectral acceleration. This is response accelerations I am talking about. Then, let us look at the energy. So, at any point of time, total energy is constant. So, total energy is equal to kinetic energy plus potential energy. But in the oscillating system, in dynamics, usually what happens is when kinetic energy is very high, potential energy is very low. Okay. When potential energy is very low, kinetic energy is very high. So, it is like that. So, that means what? TE, total energy, is equal to KE max. Like that, total energy is also equal to potential energy max. So, that is the relationship here. So, kinetic energy maximum is equal to potential energy maximum. Both maximums are equal. So, if you look at this graph, this is 0 displacement time but high velocity time. This is maximum displacement time but 0 velocity time. So, these are reverse of each other. So when displacement is maximum, velocity is 0. When velocity is maximum, displacement is 0. Now if we apply that here, half mv square is the maximum kinetic energy, that is V max. If we take potential energy is half k u square, so u max, okay, the displacement. Then if we substitute it, the spectral values, mass into s, spectral velocity square is equal to stiffness multiplied by spectral displacement square. So from this what we can conclude is spectral velocity square is equal to 1 by k by m into spectral displacement square. If we take out the spectral velocity only, then what we get is spectral velocity is equal to under root k by m, so that is omega spectral displacement. So you can see this one. So spectral velocity is equal to omega times spectral displacements. So now if you look at all the cases, yeah, this case, special case, you can see this one, spectral velocity is equal to spectral displacement multiplied by omega. So that is spectral velocity is equal to pseudo spectral velocity under this situation. And for similarly for lightly damped case also same thing. And for stiff systems, now we discussed about damping. Now let us take the extreme values of period. So for stiff systems, that means what? So T is equal to 0. So that means rigid system. So omega natural frequency is infinity. So they are reverse of each other. So as the oscillator system becomes very stiff, it does not deform and moves with the ground. Hence maximum relative displacement and velocity are quite small. So it is something like this. If you look at this one, this is very stiff system. So whatever motion I give, so base motion is equal to the motion of the mass at the top. Same motion, no change in the motion. So you can see that there is no relative displacement between base and the top. So that can be illustrated from by seeing this figure. So this one, it is very stiff system. If I move this, okay, by some acceleration, same is the movement. So there is no relative movement between the base and the mass. So that means what? Spectral displacement is approximately 0. Spectral displacement is what? Deformation in the system is spectral displacement, that is approximately 0. So there is no, and spectral velocity is also 0. There is no relativeness. Velocity also comes from the relativeness of base motion and the motion of the center of mass. So that means what? Spectral acceleration is exactly equal to ground acceleration. Whatever ground acceleration is given, that is equal to spectral acceleration. And another special case is when T is infinity, very flexible structure. Okay, that means omega is 0. So as an oscillator system is very flexible. So when ground moves rapidly, the heavy mass does not get chance to move. Its absolute acceleration remains 0. It is something like this. So when I am moving the base here, mass is very heavy, so it is staying here only. Base is moving but mass is staying here. So why? Because this is heavy mass, it is not getting chance to move because of the rapid movement of the base. How does that look like? It looks like this one. Very heavy mass, base is moving without motion of the mass. So that means what? Acceleration of this mass is 0. Whereas spectral displacement is Ug max, whatever is ground displacement, that is maximum value, and then spectral velocity is also maximum value, ground velocity value. So for zero damping case, spectral acceleration is equal to pseudo spectral acceleration, spectral velocity is equal to pseudo spectral velocity. For light damping case, spectral acceleration is equal to pseudo spectral acceleration, spectral velocity is approximately equal to pseudo spectral velocity. For flexible systems, acceleration is equal to maximum acceleration, ground acceleration. For stiff systems, spectral displacement is equal to maximum ground displacement, spectral velocity is equal to maximum ground velocity. So in this class we have studied about the special cases of response spectrum which can be made use in the application of response spectrum to design of structures.